legal expert to somebody who's working in the medical domain to somebody who's sitting and trying to play with the system, right? So we have wide variety of users, and every users would want to know why exactly was this decision made, what is the rationale behind this. Good, and that is what is called as the explainability, right? And then I'll try to take a use case of face recognition, and then I'll try to talk on a couple of topics of explainability, and then you can generalize it for different areas. So what I'm not going to do is that I'm not going to intensively talk about what is called as class activation maps, which is based on gradient. I'll just introduce it very quickly, but I'll go a bit deeper into the new direction that we have been working in the last couple of years. Good. So if you kind of plot everything that is available today, I took this illustration from the link given there. You see that you have all these models such as neural nets, deep learning, graphical models, everything that is having kind of intersection, right? So here, up in this area. And then you have this prediction accuracy, which is quite high. And then when it comes to explainability, they're quite low, right? So you get either one or the other, not both at the same time. So the recent works have been focusing more on making them more explainable. And what would that mean? For instance, if you take a deep network, right, you want to modify the learning techniques so that it can also become explainable. And how do I do that? I start playing with the gradients, right? So we back propagate the gradients, and every time I do this, I could take out some part of the gradients. I could create a class activation map, which I already showed yesterday. And then if you go to the other set of models, you have this techniques which are more structured, in the sense that whenever I'm creating a random forest, I know exactly which tree is activated, which node is activated, which leaf is activated, right? I do the same thing with the random forest. SVM, probably to some extent, I can explain the hyperplanes, where the hyperplane is lying. But then the models are very weak. They don't generalize, right? So that they tend to overfit sometimes. And then you have this other ideas where they talk about this model induction, which are kind of techniques to infer some explainability from a model, given that it's a black box. So what does that mean? That means that tomorrow, if Mahipal is selling me a system, I don't know how he has designed the system. I only know that there is an input, there is an output, right? So typical black box scenario when many companies sell this to us. Now, what we want to do is that we want to take this as and explain it as a post hoc methods, and this is what we call as post hoc methods, right? I don't have any knowledge about the model, or I have partial knowledge about the model, and then I build something on top of that so that it becomes more explainable. So if you can make an analogy, what you can see is that you can start seeing that whatever the model is there, on top of that I build another surrogate model, and these surrogate models are typically trained to be explainable, right? Give some initial ideas. Okay, so now I want you to think about at least a couple of things that we have been speaking about in the last couple of days. Any techniques that comes to your mind? Not in the post hoc, maybe in the other sense. Anything that you might have seen in the past couple of days as an example, or something that you might think will work?
The graphs which we are making for something to understand that why outputs are generated in different ways. Can be one of the ways.
The images that you're talking about, the colored images?
Yeah.
Yes, right? So let me just pull that slide for a short moment, and then we can go back to this slide just to give you an idea of what I'm talking about. You all remember this graph? This figures from yesterday, right? I did not discuss this very in detail, But I showed you that this is something that we use for explaining the decision making of the system. So what is that I'm doing here? So every time I have a deep neural network, so I have a couple of layers. So this is my input, and then I have layer 1, layer 2, and layer 3. That's it, right? And then I have an FC, and then I have outputs. As simple as that. So now, in each of these cases, we are aware that there is a gradient, right? So when I've learned the whole system, this is nothing but a matrix, right? It's a series of vectors, series of vectors, series of vectors. So if I've learned a system which takes an image into this, and then it creates the gradient, at one stage, I would stop updating this gradient. Make sense? And then I don't do anything more, right? So now I know that my system has learned properly. At this point of time, I could say every new image that is passing through this, and this gives a response map, right? So whatever the image I have given, it will be, let's say, some areas activated here, and in this one I have another areas activated here, right? And then in this one I have another area which is activated here. Simple example. Now this is what is called as class activation maps, which is derived from the gradients. I also took another example of the
Question from my side. So, when we were training the model, then we are like back propagating the gradients,
right.
right?
Yeah.
Once the model has been trained, then at inference time, when we pass the image, so yes, at every layer there are going to be activations,
Right.
right? But at that point in time, we are not computing the gradients.
No.
But then why is it called GradCam?
Oh, why is it called GradCam? Because it's typically based on the gradients.
But how?
Because it's this one, right? This weight matrix is nothing but the gradient, right? It's the frozen gradients.
These are the frozen weights.
Frozen weight, yes, based on gradients, derived from the gradients, right? So you back propagated the gradient to come to that weight matrix, right? And that's why it's called as gradient cam. GradCam, sorry. That is one category, right? And then there are a number of different categories, which I'll give you some names here. GradCam, and then there is ablation cam, then there is score cam, then eigen cam, and many.
Lime, Shapley.
Lime is exactly what I'm going to talk about today, right? So I don't focus on this family. I don't focus on Shapley because it becomes too broad, very detailed. So I'll focus on this one. But everybody got an idea about what we're talking about cam, right? So now, what is the difference in the regular grad cam and ablation cam? So the only difference is that we do ablation, right? What do we do in ablation studies? We study the parameter invariance. If my network has 3 layers, let's assume my performance is 90%, and somebody might be curious, and they might come back to me and ask, what happens if I take only 2 layers, right? So then I'm checking the how much does my network vary or how much does the performance vary when my network varies, my parameters vary. So which is typically called as ablation study. So maybe it goes to 80%, maybe it goes to 90%, 95%, and so on. So when I've established that, I can say that my network is very stable whether you put 2 layers or 3 layers. Right? So that is typically the ablation studies. Now the same idea is used in the ablation camp, where what they're doing is that they ablate the different kind of images and then get the explanations. And the explanation that you're getting, the cam maps, is now kind of an average version of that. Give some initial ideas. Okay? So there is a ton of implementations for this. You could just go there and then start using them. It's not a problem. And then there is this second one, right? Which is, I think I should also mention the strength of this eigen cam. So yesterday we also spoke about the subtlety of this networks. Whenever I have some small changes, the network can give me very diverse results, right? Which means what is happening? Every time there is some small change, the gradients kind of shift a lot, and then the explanation that I'm going to get, sorry, not the explanation, the CAM that I'm going to get might shift very much. Now, go back to your math, first semester mathematics. Most of you did this eigenvector derivation. So you took a matrix and then you took only the ones that were stable. So if I can do the same principle here, so every time I'm changing some input, then I'm trying to see, okay, what exactly is the one, what are the elements that are remaining consistent? I can derive this as an eigenmatrix, right? And that is the principle used in eigencam. Good. Okay, and now let me ask one other quick question. I was showing you some transformers yesterday. Do you think the CAM is a good concept to apply in transformers?
No gradients there.
There is no,
gradients.
there are no gradients, okay. One good argument. So you say that it's not a good idea to apply there.
But if it is working on base,
Yeah.
then can it work?
Any other ideas? Okay, I take your point. Any other ideas? Let's see. I showed you, in fact, on the fingerprints, right? I showed you that I use vision transformers, and then on top of that, I showed you class activation map. But there is a fundamental limitation with that. Anybody thought about that? How about the fundamental difference that we spoke about? We spoke about the CNNs being very good at local receptive fields, and transformers being good at the global context. So if that is the case, then how relevant is this CAM for transformer architectures? It shows something, but is it the right way to do it? No? Yes? No? At least I believe it's not the right way. Because in the initial days when we were doing, we were just taking the CAMs and then we were just putting it on every single possible thing that was available. Because there was no tool available, right? So we were just looking at the gradients, weight matrix, and then trying to show, okay, this is what the network is looking at. So in theory, if you look in a broader perspective, even if you look back at the work, that was a wrong thing that we did. I would not say it's the wrong thing, but it's like it's not the right approach. There are better approaches for transformer-based architecture. Okay, that's a bit of a side story. Now, that means that there is a lot of scope for you to look at explanation methods for transformer approaches. So not too many works have been published in this direction, right? And then comes the second part, right? Now this class activation maps, I could use it for many different things. And I showed you that because the internal working of the architecture, the class activation maps are not really explainability, are they? Is it explaining something or is it just highlighting, okay, this is because of this? It's not giving me any reasoning, right? It's not telling me anything about the image. It's just telling, okay, these are the areas that I've used to make the decision. That is more like visualization. It's not really an explanation. Okay? So now we are talking about two different aspects. One is the interpretability, and the second one is actual explainability. Back. Good. And then comes the first idea of how about making it both interpretable and trying to be model agnostic. Now you can already imagine, right? If I use ResNet, probably I get a class activation map which is activating this area. In the other case, it will be something else. If I use LXNet, it will be a different area, right? Now there is nothing wrong with that. It's just showing what has been activated in those particular networks. But that means it's very dependent on the models. One, it's not really explaining, it's not really interpreting, and the second one, it's actually explaining. It's visualizing rather than explaining. Now, how do I make it explainable? So there is this approach called as local interpretable model agnostic explanations. It's a technique that kind of explains the prediction of any machine learning algorithm. So it's not necessarily related to your deep networks, but it can also be related to your simple classifiers. And then the idea here is that it kind of approximates the model locally within a bigger model called interpretable model. And the advantage or added advantage is like it's also kind of helps you in understanding why a model made a certain prediction, not the other prediction, right? Why do I say that this is a cat instead of just saying this is cat, right? The why factor comes into the picture here. And how does the line work? Uh, I'm just taking the example of the images, but it can also be applied for the tabular data. Tabular data is much easier to handle with rather than the image data. Okay, and now we can also generalize some of these arguments for sharp-based explanations. Okay, so what does it do? It takes the image and it divides into number of components, and the base here is that it divides it into number of interpretable components. Which means if I'm talking about this face image, what I'm going to do is that I'm going to divide them into left eye region, right eye region, nose region, mouth region, chin region, forehead region. Right? So it's again just dividing the whole image, whatever the image is, you are going to divide it. And that's an hyperparameter. I'll talk about the hyperparameter in some while. And then what it does is that it takes a particular block. Let's say it says, okay, I take the image of Kiran, I don't like his eye, and then I block his eye first, and then I try to explain, is this Kiran? And then I do the same thing over and over again and get all the different predictions. You get an idea? So is it still Kiran if the eyes are not visible? So I'm just perturbing this one, right? That's what we call it as perturbation. So perturbation is nothing but adding some bunch of noise there. It could be as simple as a black noise, which is nothing but black pixels. And then I do this approach, and then I get a prediction score of let's say 0.8. And then I do it for the next region, I get another 0.7, and so on and so forth. So if you keep on doing that, you get a bunch of different prediction scores. Now, if you have this all prediction scores, you can try to explain, okay, it was telling it was Kiran mainly because probably the mouth region was different. So this is the intuition. I'll explain you in detail what are the working mechanisms, but you got an idea. Did you all get an idea on line?
You said it is workable on the ML also.
It's workable on. In fact, it comes from ML.
Suppose we have a random forest
Yes.
model that can work on that.
Yes. The base comes from those classical machine learning. It was adopted in deep learning because nothing else was. Not too many works were being published in this area. So line comes from classical random forest SVM. Okay, so the intuition is fine. Everybody are with me? Okay, good. So now let's see what exactly happens. Let's start with this image, right? So every lecture should have some cat images, and here is my cat image. And what I'm trying to do is that this is the first thing that I mentioned. We need to divide it into superpixels. Now, superpixel is a particular technique that is used for dividing the image into different segments, but there is no hardware what it should be a superpixel segment. It can be any of your out of the box segmentation tools, or you could simply sit and mark the boundaries yourself. And this is slick based superpixel segmentation, which is nothing but again another thing that is taking care of locality of the neighborhood. Right? So what do I say? Why do I say that? Let's take the example of this particular area, right? The watch. So you're not going to put it in two different sectors. Not partly with the what do you say the strap, and not partly with the other one. For instance, I don't know if I'm making sense, but let me try to draw a simple segmentation here. So this segment is here, right? And now it would have been not a good idea if I segmented it like this, and then another segment like this, right? So you take care of the locality in the first instance, which means I see that, okay, the pixels in this area are belonging together, so they should be in one region as compared to the other one. Okay, so this is the beginning of how I make sure that the locality is preserved to explain anything. So when I do this, after doing this, what I do is I perturb one area. So what do? I perturb, let's say, this area. So I mask it out. I put it with black pixels, and then I get a prediction. So if I mask that area out, that should that really change any prediction of cat? In theory, it should not, right? So if it does, that means that that area is not reliable. So I should not be telling that the system is explaining it's cat because of the skin area there. Okay, and then you could keep on doing this for multiple segments. Now, how do I determine how many segments I do? What is a golden number? What is a magical number? That is something that we'll have to figure it out. Yeah, I'll come back to that in a short while. But the whole intuition is this.
We have segmentation algorithms.
Yes.
Right? So can we use those, or are we using those over here, or can we use those over here?
Yes, you can use those. So as long as you can somehow guarantee that the locality is constrained, you can use any segmentation. In fact, our experiments in one of the work already showed that using the domain-specific segmentation is much better for such kind of explanations rather than doing a random segmentation. Right? So if you have something, start with that. Okay. Good. So what the reason why we go for superpixel segmentation is because it's something very generic and it's been well tested in a number of different applications. That's the only reason why we go for superpixel segmentation. Okay, so if I keep on doing that, right? So what is it going to tell me? It's going to tell me that if I use these areas, the areas that are marked in the green, they are the ones that are contributing to tell me that this is an Egyptian cat. Now, is there anybody that can find some problem with this one? Any idea? The color, yes. The color is highlighted, right? But it's telling that based on the color that is given here, this kind of green area, it's telling me that it's the Egyptian cat. But does it make any sense? To some extent, yeah. I can see that there is a fur, there is fur here, and then there is tail here, there is the ear of the cat. Yes, I can assume that it's a cat image. But there is also some small fundamental limitations. I don't know if you're able to see that color on the side. I can see that.
So the part of the watch is also
The
coming.
part of the watch is also coming
Green.
here, right? So you can see that small area that is being highlighted, right? So now, why should the watch become a part of the cat? Cats do not wear the watches, right? So it kind of semantically does not retain any meaning. Okay, so then that's what we are talking about, one class. And now I could also say that, okay, try to explain it to me if it's a tabby cat. Tabby is another kind of race, right? So in this case, it's telling me the probability of this being a tabby cat is 0.15. And then the areas that I'm using to make the decision is the area here, which is only this area.
Why is that?
Why is that?
Why is it using only that much area?
That's how the localities. That's how we are fitting the whole classifier, right?
And what is this explanation fit?
The explanation fit is nothing but your line. How close is to the explanation? So the linear classifier that you want to create, right?
So the probability is that it is a tabby cat is only 0.15.
0.15.
That is possibly the confidence
Yeah.
of the model in predicting.
Right.
But and explanation fit.
It's the measure that we are using from the line model itself. I'll explain it in a short while, right? But you get the intuition here that the area that should be used for telling that cat is the Egyptian cat at least should not include the watch. Okay. So how does it essentially look like? It looks like this one. So these are the areas that are being used for telling that this is the cat image. And then the second one, it's also telling that these are the areas that are used for telling it as the tabby cat. And then there is all the other areas which is ignored, is the area that is grayed out. Now, if you take a deeper look into this, there is also second concept. The second concept is that I showed you that every time I blurred, my prediction goes down. This was my simple assumption. And there is no guarantee for this. Right? How can I be guaranteed that removing one area will always decrease the prediction? Maybe if I eliminate this mouth area, my prediction probability would go high. Right? So which means that this is something that was negatively contributing. Right? You understand the intuition? Something I remove, then the prediction probability increases. That means that that area was negatively contributing. And if I remove the areas that are actually contributing to the prediction, then the prediction goes down, which means they are positive contribution. So now we divide these contributions into two different aspects. Now, if I try to look at it very closely, so I see that the areas that are kind of highlighted in the green are the areas that are used for the prediction, out of which the positive contributions, and the ones that are used in the red area, they are the negative contribution. Gives an overall idea. So we said there is some components which are contributing, and now I'm telling there are some contributes which contribute positively, some which contribute negatively. Right? At a very high level. Okay, that means now there is no guarantee on about there is no guarantee about which area that would be, right? So if I run it for 10 times, there is some metric that I'm going to get, and if I do it for 20 times, I get a different, completely different metric. Then there are two fundamental issues with this one. The very first issue is that if you look at this image which I was taking into example, I said that I'm going to remove some region. Now, how often do you see a person where the face image, where the one complete area is blacked out? Does it correspond to the real world? It doesn't, right? So what does that mean? That means that we're not taking care of the semantic meaning. Okay? So which is exactly the first problem. Then the second problem is that what is the gap? You can also perturb it with different factors, right? So now one is randomly taking it out, and the second one is inserting the random pixels there. How relevant is it putting the random pixel? For instance, maybe if I have this cat, if I insert some random fur here, in this case, instead of this brownish fur, if I introduce some black fur, maybe it makes some sense. But if you introduce some green fur, then it doesn't make any sense, right? Unless the cat has been painted by somebody, right? So which is very unlikely. So what we're talking about is keeping the contextual meaning and keeping the semantic meaning. So the two fundamental problems is this one, right? So one is I cannot randomly keep on inserting this black pixel, making all this area to be deleted. And the second one is this one, the blurring, the randomly inserting any kind of color doesn't make any any kind of sense at all. Okay, so I kind of motivated that there is a better way to use the line, and it works very simply. And then I told you that there is a fundamental problem with that. Okay, so now how do I solve this one? So let's start with something very trivial, right? Let's start to understand what is the base problem here. So one base problem here is this one, right? If I take a network and if I ask you to explain it to me using this lime approach, and then I see that I told you there are positive contribution, there is negative contribution based on the prediction probability. Now take a closer look at this image. This one, right? So let's just focus only on the top row, and then we can generalize it to the bottom row. When you look at this one, do you see if the region 1 is consistent in all the 4 runs? So these are 4 runs, right? I mean, I can run deep model multiple times. So I run first time, and then I try to get the explanations using Lime, and then I run the second time, third time, and so on. So in the ideal world, that should not change. But in Lime, it does change because of the neural networks, yeah? So do you see that the region number 2 is also remaining more or less consistent. Region number 3 is also consistent. What about region number 4? 4 and 5 are not consistent, right? So they are flipping across different runs. And now take the same idea for the next one. There you see that it's telling the POI is the top 5. This is the top 5 contributors for the predictions, which I'm showing. So in the top 5 negative contribution, it tells me that POI is the top 5th in the first one. And in the second one, it says, wait, no, that is not true. Now it's the region next to the paw. That is the top 4 contributor for me to tell that it's a cat. And then it goes further and it flips again and tells, okay, no, it's 4, that's paw. And in the next one, it says, well, forget about what I said. Now it's a completely different region. Right? So now you kind of see the inconsistency, right? So if I have to explain this to a patient in a medical context, if I'm using this, so what I'm going to tell him? I'm going to tell him that, wait a minute, you have COVID because I see some stains here. And then some other doctor comes and says, okay, forget about that. There are no stains. You have COVID because you have a golden chain on your neck. Right? It doesn't make any sense. There is no context here. So how do we solve this problem? So first problem is that Lyme does not inherently keep context, and the second problem is that it's inserting random noises and does not respect the semantic relationship. Now we can solve this one, right? We need to solve this, and again, I'm just taking the example of Lyme, but then there are variants which are called A Lyme, D Lyme, B Lyme, S Lyme, and so on. So which are all formulating the same idea in a slightly different manner. I don't think I'll be able to introduce all of those, but you get the idea, the working of this area. Okay, so now how do I make sure that I retain the semantic meaning? That's the first problem that I need to solve, right? So let's try to take a look at this one. So what I'm saying that instead of randomly inserting some pixels, what if I do blurring? I could do that, right? I could simply blur one small area, which means that the semantic area still remains the same. I'm not impacting the semantic area, but I'm slightly changing the information, which is still within the context of the whole image, right? So which is nothing but I'm blurring one small area, for instance, this one. Let's say this area. If I blur this area, the leg is still there. I'm not deleting it, but I'm just making it subtle. And then I can measure the probability, right? So for that particular change, I measure the probability. Now you see there is a X and Y matrix that I'm creating here. So where I'm saying, okay, I blur it with a small factor. Let's say the sigma equals 0.2, which is nothing but the Gaussian blur, right? So in the Gaussian blur, we put the kernel size, we set the noise, the sigma value to say what kind of noise I want. With sigma equals 0.2, I get the prediction probability for each different run. So the first time I'm taking all the regions, and I'm seeing that the performance is 0.925, the prediction probability. And then what I'm doing is that I'm making sure that the segment number 1 and segment number 3, 1 and 3, they're taken off, they're perturbed using the Gaussian blur, and then I see the prediction probability. Right? So if I keep on doing that, in one case I see that, okay, there is almost no change here. The prediction probability is remaining consistent. Now, since I have this framework already available, what is stopping me from perturbing multiple times with different configurations? So I keep on perturbing it using different configurations. I see that, okay, with sigma equals 0.6, I get different prediction probability, and again sigma equals 1, I get different prediction probability, and so on. Now, if I have all this bunch of prediction probabilities, I can start saying, in the original image, this was saying this was a dog, and with a probability of 0.799 without any perturbation. And now with the perturbations, I see that it's increasing, and then at some point of time it's also decreasing if you extend the table. Okay, so far I have not done anything other than introducing something like blurring to keep the semantic meaning. That's the only contribution, right? And now, how do I make sure that which one of these sigma parameters to use? So I can have numerous combination of this one. So where do I stop? So for that one, if you do a simple sigma value works in PDC that we did, you see that for sigma equals 0.01 around 0. So the variance is quite wide. It can go all the way from 0 to 1, the prediction probability, which means that it's not very reliable. And then if I increase it to 0.1, 0.2, 0.3, 0.4, and so on, you see the prediction probabilities kind of become more stable in this area. And then after 0.6, it kind of starts changing. It kind of indicates if I'm going to use the blur for my approach to make the explanations more semantically meaningful, then I can say use anyone between the area of 0.1 to 0.6. And surprisingly, there is a theory which also relates to the fact that sigma equals 0.3 in the Gaussian blur also relates to the human visual system. So there is this paper from psychologists where they introduced some different pictures and then they showed them these pictures with different blur values. And at 0.3, it exactly correlates to what humans would see. Okay. Anyway, so that is now the part 2, right? So I now solve the problem of this semantic consistency. Now let's take a step ahead, right? Why should you trust me? I mean, why should you trust me that, okay, the semantic meaning would be consistent? So to measure that, what we kind of now say is that, okay, let's assume that we have this particular table. And in this table, I can see that the prediction probability is either positive or negative. If I take a difference between them, so there is this difference between this and this, this and this, this and that. So every pair, then I'm going to get a vector which represents either positive change or negative change. Gives an idea? I'm just taking a difference, right? From base prediction to all the other predictions. So which is a new vector. And now using this new vector, I can start measuring how many of them are actually flipping. Right? So I don't know if I should simply write it down here. So the base probability 0.75, let's assume, and then for every different configuration, I'm going to get 0.65, 0.7, 0.9, and so on. So now if I take a difference between them, then what is that I'm going to get? 0.1. Between them, between this and this, 0.05. And between this and this, I see 0, minus 0.3. Make sense? Nothing other than just taking the absolute difference, right? So now if I consider these as a set of vectors, a number of elements in that, I can see that if I keep on doing with different vectors, then I'm going to get multiple configurations of this one, right? So as long as I get that, let's assume it was 0.1, and this one was 0.2, this one was 0.1, and then let's assume this was 0.02, 0.1, and minus 0.3, and then let's make it minus 0.25, and let's make this hypothetical number 0.15. Now there is something happening here, right? So the thing that is happening exactly is that these are all in the positive sign, the first vector, the first elements. The second elements are also in the positive sign. And the third element, there is something happening. The sign is getting flipped. See, it was negative, positive contribution, suddenly it became negative contribution. So that means this element is something that I can't trust. Right? Or I should not be taking that, I should not be putting my trust too much into that. I should make it a little less in terms of weight. So if I now measure all the entropy of these new values that are computed, which is nothing but the ASFE, right? The score that I'm saying there up on the top left corner. See, it's an average version of for a given model, for a given explanation method, if I'm averaging it out across all different runs and I see how many of the signs are flipping, then I get a particular number, which tells me, okay, how much is this changing as a function of this Gaussian blur, which keeps the semantic meaning. Okay, good. And then now again, what is that H sign? H sign is nothing but the classical entropy formula from Shannon's information theory, right? It's the minus P log P minus of P2 log P, log 2 of P, right? Which is the Shannon entropy formula, which it could be any other formula for that matter. I mean, the whole idea is that we want to capture how many of the signs are getting flipped. Okay. Good. So if I do that, and then I could also extend the same idea to the. You remember I also told you about the segments. I'm going to start with the segments, and if I have these segments, I could also make use of that segments, which means I could also see for each region, this region is going to be consistent. This region, this region, this region, this region, in the same part for different images with the same seed of segmentation. How much are the regions flipping? How much are the ranks flipping? Right? So which is nothing but all these things we were talking about, right? So we were telling about this 4 being flipping, flipping, flipping back again, flipping again. So that means that is the rank of the segmented regions are also playing some role here. So what my goal is now is to capture the relationship there as well. So what am I going to do? I'm going to do this rank correlation, this part, between the segment I, the region I and region J, and then I kind of average it out for the entire, all the combinations. And in this case, how do I measure the rank consistency? It's, in this case, we used rank biased overlap, but if you have even better method, sophisticated method, you can use it there, right? So by introducing this, I want to capture the consistency and I also want to make more stable. So what do? I put both of them together in this formula here, and I say what is the cascading effect of them? What is the probability of both happening independently, right? So if I take it as one factor not impacting the other factor, I can multiply them. So which is what I'm doing here, right? So I'm taking this score, I'm taking this score, and then I'm multiplying it here. So when I do that, I get something called as a combined consistency measure. So the whole idea was that Lime was inconsistent. Now I'm trying to make it more consistent. So this measure captures the combined consistency. Okay, so if you put everything together, what exactly is happening is that a simple solution by introducing blur. And then here there are a number of things, right? One thing is how do I make sure how many times I should run the model? Should I run 1000 times, 10,000 times, 200 times? I don't know. So that becomes a hyperparameter, which is here. And then I can also say how many iterations it should run. And then in this case, you can see how the algorithm works. But remember, everything that we are doing is we are doing in a bootstrap manner. There is no probabilistic model here. So which is by itself a problem, right? So I have no control over how many iterations I should do. So now in the more recent work, there is this variant where we are trying to formulate it as a Bayesian context, which bases more on likelihood. Okay. Okay, you don't have to drift away so much to that, but the you get the whole intuition, right? What I do to keep the semantic meaning, and then how many times I run, and then how do I determine what is positively contributing, negatively contributing, and then I can explain the model in a better way. Okay. Good. So what does this? What is the independent contributions? And then we benchmark it with different other approaches. For instance, here there is Lime. In the case of Lime, you see that the prediction probabilities or the consistency scores are very, very low, somewhere around 0.22. And the consistency scores of the proposed approach, which is based on this semantic retention, semantic meaning retention, is somehow consistently around 0.997. Right? So it kind of shows that this approach captures things very well. And then if you measure, and then, okay, what is the contribution of each of these different things? I said it captures two things. One is by blurring, and the second one is by making sure that the features are eliminated. So now I told that I need to put both of them together to have a better method. So what is significantly playing the role? If you look into this, you can see that it's in fact blur that plays a significant role. And this somehow intuitively makes sense, right? So as long as you're able to keep the semantic meaning, irrespective of what method you are using for rank correlations, irrespective of what method you are using for eliminating the features, they will be not playing such a significant role. Okay, so here you see that they actually all come together in one slide, where you see the effect of this blur is captured here in the experimental setting, which is exactly what we are seeing here. So as long as this is consistent, the contribution to explain any particular approach where Gaussian noise becomes interesting can be very evidently seen here. Now that also opens up a new avenue, right? So the new avenue is that why should it be only Gaussian blur? Why can't it be some other kind of perturbation? So there is another, if you look into the paper, you can see that we also studied some different kind of perturbations. Some of them keep semantically relevant meaning, some of them do not. So you can, if you are interested in this direction, so you can go a bit deeper. Okay, so what did I achieve with all those story that I was building? Now you see on the top there is Lime, which is the existing approach, and Slice is the stabilized version of Lime, which came out last year. And in that case, you see that although the areas are whatever the areas that the network is saying, they are still remaining consistent. The head region 1 remains 1, 1, 1, 1 at the same location. And then it's 2, 5, 4, 3, 2, 5, 4, 3, 2, 5, 4, 3 is the same. And when it comes to negative contribution, again, it's 2, 1, 3, 4, 5, 2, 1, 3, 4, 5. It's always the same order. So all we did was not to make the network give me something new, but to make it consistent. Because remember, you have a model that is given by somebody else, and I do not know who this vendor is, but I want to have a ad hoc method which is on top of this existing models, which should tell me why exactly I'm saying this is the areas used for explanations. Okay, so how much time do I have? Okay, should I just introduce you? When is the break? Yeah. Okay. Okay. So you're all still with me. So should I now show you an use case from a different angle? So this was from the explanation part, right? Where I showed you slice, and then okay, the bigger problem here is that although I've been telling nice things about this method, there is also an inherent problem, which means it takes longer time. Every time I need to do all this perturbation, every time I need to run it to multiple iteration, it's going to take me at least like 10 times more than what it should take. Right? So which is already described in the paper, and then that means if you are going to use it for a system where you have to make quick decisions, then this would not be the method to use. But this is still consistent, so it's a trade-off what you want. Okay, good. And then there is a new work for this, which is called which we call as belief, which I did not include here. But there we are putting it in a Bayesian context, and the running time becomes 10 times slower. So it's also, or let's say 100 times faster. Good. Okay. So now let's take another problem, right? Let's take, this is something that I'm going to introduce you the idea. So if you are interested in taking this area, you could look into this direction. Okay, so this part of the talk will be based on two papers. One is called as Coffee, which was published last year. It is called Consistency-Driven Feature Elimination for Explainable AI. And then I'm trying to use it for something else, which is called face image quality, right? So I'm now trying to connect different components on how explanation is connected to the quality. Let's start with this one, right? So here is typically how your system is designed. So you have a face image, and then you want to put it into the system, and then while you are doing this, you want to estimate the quality. If the quality is not of a good value, then you would want to say that, you know what, try to recapture the image again. right? So this is to ensure that there is a minimum quality that gets into the system. And then there are a lot of standards, right? One of the standards is that, okay, there is this ICAO standards and this entry exit system in Europe, which also talks about how the face image should be, what should be the standard pose. You should not be smiling, the hair should not be covering your face, the sunglasses should not be there, and so on. So all of these kind of give you a guideline, which system to an explanation system. I'll not get into these topics, but just to give you an idea, here you can see that the quality measure itself can level. What I'm saying is that if I'm taking a picture where the light is coming on my right side of the face and there is no light to the left side of the face, that means it's non-uniform illumination, right? So there is one of the image, the whole quality of the image. So there are two things, and then there is the capture related, and then there is subject related, which means the first one, the illumination, what I said was capture related, and the second one is subject related, which means every time I'm trying to give a picture, I might be crying, or I might be smiling. So which is non-standard pose, right? So you want to also detect that one. So I'll skip a lot of these other examples, but just to give you an idea. So the unified score you are trying to see is that 0.7, 0.8, and so on. And in the case of the capture related area, you see that it's blurred, the eyes are not open, it's underexposed, and so on. Okay, let's forget about all of these things. Now let's go to the simple approach, where we are trying to look at this, the whole idea of how the quality factors influences the performance. So it's a measure that I'm using, and I'm changing the quality metric, quality factor every single time. I'm trying to eliminate 10% bad quality, and I'm seeing how much does the error rate drop. So in ideal sense, if I remove all the images that are of bad quality, the performance should be very high, right? Which means it should come close to zero. Okay, at a high level. Okay, this is just an example that I'm trying to give. And then each of the component have their own role, right? So sometimes maybe the smile is the one that is impacting so much. Sometimes it might be the illumination that's impacting so much. So what I can do is I can use all of this and then learn a meta model which kind of estimates, given all these components, what is the final score, final quality of this image, right? So the smile ratio is 0.3, the illumination is 0.4. Let's assume the background noise or background whiteness is 0.2. With given these values, what is the overall quality of that image? So that is nothing but a simple SVM like classifier. So once I have that, any kind of new image that I'm going to get, if you're capturing it from your smartphone, I can tell you that, okay, this image is of not good quality because I have these many factors, these many small values, which is leading to that. But what is the problem? There's a fundamental problem here, right? So one is, if you look at different databases, you start seeing that in some cases, it's telling that some quality factors play a good role. In some other cases, it tells me that they're playing not so good role, right? Now, if you link it back to the ideas of this line that we're talking about this positive contributions, we're talking about negative contributions. Now, if they are consistent, it's fine. The problem comes when they are not consistent, when they're flipping. In one case, it's saying focus is an important factor, and in the second case, it's saying no, it's not focus. Focus is not so important factor. Okay, so what we want to do is that we want to now make it more stable, and the problem also comes in the second aspect. It is somehow not consistent across different models, the face recognition model. So if I'm using arc face, I see this kind of trend, and then if I suddenly put in some other kind of network, which is, let's say, FaceNet, and then the trends also start changing. So I'll not get too much into the details of that, but just to give you an idea, what we want is that we want to achieve something that is more explainable, like this. Here is the example of Shapley, right? You are asking me about Shapley. So this is typically the example of Shapley. So which is telling me how much each of these factors is contributing. So if you look in this particular example, there is this data set called as LFW, label faces in the white. and there it seems defocus is the prime factor. Right? It's telling me that's contributing very highly, and then it's telling me if the face is horizontally shifted towards right, it really has no impact. Okay? So now I would be very happy if this was consistent across all the data sets and all the models. But in practicality, what happens is that it's not like this. And the other aspect is that if I'm taking only top 7 features, they are there, defocus, mouth close, and up to sharpness, I can still get the same performance as I would get using all the features. So it kind of tells me that I don't have to compute all the other features, right? They're useless in some sense. But as much as I like to remove this one, if I'm telling you that if the eyes are not open, I will still accept the image. Would you be happy as a passport issuing officer? No, right? So although it says that it's not very important, it has a significant role. So I want to retain the inherent meaning of that in the context. Okay, so what can I do? I can do again go back to this the idea of gradients. I know that the gradients tell me something, and I can introduce some kind of pixel level quality computation here by taking the face recognition model, any model that you have, and then look at the gradients and then try to measure how much the probability is flipping by looking at these embeddings, and then I can connect it back and then back propagate it now and then estimate all the gradients that were changing across different settings, right? Setting number 1, setting number 2, setting number 3, and so on, and then you add them up, and then I can tell, okay, these are the areas that I'm using to tell this is the quality of this image. So this was one of the early works that we that was done by one of our colleague. But the problem here is that now we are introducing a very strong dependence between the network and the method. So it kind of assumes I have the complete knowledge of this network. Right? So tomorrow, if a new network comes, then I have to still retrain this. It does a good job, but then the downside is just that you have to retrain it all the time. On the other side, right, what we want is that we want something like this. If I take a picture, I should say I'm not accepting it, and then the user should not be completely confused. We want actionable feedback, which is the goal of this explanations, right? If you look at the Lime part we were trying to explain, and here we want to explain it and then tell, okay, I rejected your image because you had sunglasses on yourself, remove the sunglasses and give the image again. So that is the idea, why and how. So what we want is this, or let's say something like this, right? Now, within the explainability, as I told you that I took the example of this mouth, eyes being closed. What does that mean? That means if you take any models, the features should remain consistent. So they should not one time say that okay, I'm positively contributing, and the second time say that they are negatively contributing. So what is happening here? Feature number 1, very well, it's always in the negative contribution, which is fine, I don't have to worry. Feature number 2, I say that they're also okay. Feature number 3, you see here it's spreading from positive contribution to negative contribution. And the same here, the worst one is this one, right? Feature number 5, where it's equally likely to be positive contribution, equally likely to be negative contribution. So my goal now is to identify these kind of features which are consistently flipping, to eliminate them, so that I can say whatever I'm using for the next approach to explain the image, explain the method, will remain at least stable. And this is something that you can see for different approaches, right? Linear regression, breach regression, and so on. So again, going back to the idea of a simple bootstrapping, what can you do? You can take some number of features, number of iterations, and every time you are doing this iteration, I can say, okay, did this feature flip? If so, remove that, right? And the more it flips, the more number of time it flips, the more it's going to end up in this bucket, which I'm never going to use. So by simply doing this, what I can do is that, again, here nothing magical. If you can see, this is the same formula that I showed you in Lime. It's the formula from Shannon's entropy, right? And then I use the same thing, but I simply call it slightly different because here I'm trying to stabilize the feature. So by doing so, what I can see is that I can now see that the features become more and more consistent. And I don't think I have time to show it how it works in the quality, but now you see at least there is a small comparison with different kind of feature selection methods. It's the recursive feature selection method, sequential feed forward, sequential backward, and then the bidirectional. In all of these methods, it's the approach is being more consistent, which means if I take it to any of these features that I'm explaining, I could use this approximation, right? Okay, so I think I took 10 minutes of your break time.
That's okay.
Yeah. So any questions on this one? I know I had to rush through a lot of things, but Lime, the idea of Lime, you all got the motivation. You got the idea of Lime
Have these models already pre-built somewhere?
for the Lime and Slice. Yes, you can.
We can directly use on our images and identify that what are the errors. I mean, explainability. We can
Yes,
do.
you can. So if you, I could also give you the link. So just remind me, I can add the link to the next slide. So when I'm distributing the slide, I can give you the GitHub link. Other questions?
So now we can, what I think, if I'm creating some model, then on top of that, I can run that line model, and then I can say this is the model and this is the explainability for this model giving this answer.
Yeah. But then there are also new methods coming, right? As I told you that the Lime is some issues, and then you have variants: Lime, A line, B line, D line, Bay line, and then now another work has come from our group, which is called Belief. So
Is it available?
it's available, yeah. So it's going to be presented next in 2 weeks, and then we are already releasing the code for that. Good.
So we'll wait for tea and we'll be back.